We've been building up more and more complex examples that we can do. So we spent about 5 minutes at the beginning talking about, at some point I gave you some polls involving linear homogeneous recurrences of order 1. But these ones you guys could solve without even me telling you how to solve them. So that was things like an equals 3 an minus 1, right? So these are really, really easy, and you guys were able to solve them just by saying, okay, everything, it just multiplies by 3, so an is going to be 3 to the n times a0, whatever a0 is. And yeah, it became a little bit harder when we moved to non-homogeneous things of order 1. So order 1, by the way, remember, order 1 means that an just depends on the previous term. Linear means that it's just a constant, like you don't have, like, for example, an minus 1 squared or something. Like it's just times a constant. And non-homogeneous here now means that there's some other function being added. So this case is just the number 2, but it could be like 2 to the n or something, right? And we learned how to solve these types of things using kind of telescoping, kind of setting up a telescoping sum. Last time I talked about linear homogeneous things of order 2, for example, the Fibonacci sequence, right? And that was what we solved those using by coming up with the characteristic equation, finding the roots, and so on. And today we're going to kind of go one step above that, which is linear things of order 2, which are non-homogeneous. So that's where we're going next. So an depends on two previous terms, an minus 1 and an minus 2, plus some function of n. Okay. So the general kind of method we're going to use for solving these non-homogeneous things of order 2 is using generating functions. So this is going to be applying a lot of stuff that you learned not too long ago in the generating function part of the course. So the stuff basically from assignment 4. Okay, suppose I give you this this recurrence relation. So first of all, this is linear. The order is 2, and it's not homogeneous. So let's solve this using generating functions. So this is just my recurrence again. So the recurrence we're going to solve is where a0 is 1, a1 is 3, and generally an is equal to 3 times an minus 1 minus 2 times an minus 2 plus 2 to the n minus 2 for n at least 2. So remember what generating functions are, right? You have some sequence and you just kind of turn it into a function by making the elements of your sequence equal to the coefficients of x to the whatever power. Right, so that's what we're going to do. We'll start by just saying, okay, f of x, I don't know what these an's are, but we're going to try to solve for them using a generating function. So we just let f of x be the sum n equals 0 to infinity an x to the n. Okay, so this is just a standard place to start. And basically we want to kind of understand this function, kind of manipulate it to get an equation for an. So, okay, so here's the trick. So here's how to do this. So all I'm going to do is I'm going to start by just writing down my recurrence. So this is just the recurrence, the original recurrence, which holds for all n at least 2. So I just write it down. Now what I want to do is I want to multiply both sides by x to the n, because I'm basically trying to make it look kind of like my f of x. And in f of x, I have an times x to the n. So that's what I'm going to do. I'm going to start by multiplying everything by x to the n. So I get an x to the n on one side, and then I get these things which are not quite what I want. So I get like 3 an minus 1 x to the n, minus 2 an minus 2 x to the n, and then this thing which is even weirder, but so it's 2 to the n minus 2 times x to the n. So now what I'm going to do is I'm going to just sum this up over all the values of n. Well, not quite all of them, but most of them. So one thing I have to be careful about is that this equation here, it's only valid when n is at least 2. So this equation here is also only valid when n is at least 2. So it doesn't make sense to plug in n equals 1 or n equals 0, because, for example, if I plug in n equals 0, then I get a0 x to the 0 equals like a sub n minus 1, or 3 times a sub n minus 1, and that doesn't exist, right? So one thing is this equation only holds when n is at least 2. So I can't really sum it up. I can't really plug in n equals 0 or n equals 1, but I can do everything else. So I can just sum this up over all n at least 2. Is that okay? So is it clear why I'm summing this only from n equals 2? Because, yeah, this wouldn't make sense for n equals 1 or n equals 0. So what can I say about the left-hand side? What is this in terms of my f of x? So it's got this, the thing is it's got this an here, and also it only goes from 2. So I guess I want it in terms of, so not like an exact formula, because that's not going to be really possible at this point. But I want to say, like, if I look at my f of x, what is it like kind of compared to f of x? And yeah, so that's the right idea. This is basically the same thing as f of x, except it's missing the 0 term and the 1 term. So this is just f of x minus a0 minus a1x. And I can actually do a lot of those similar things to the stuff on the right-hand side. So, right, so here on the left-hand side, I get f of x minus a0 minus a1x, because it's basically f of x, except there's 2 terms which are missing, because this is the definition of f of x. Here what I get is, so I have 3, and then I'm going to pull out an x. And then if you pull out an x, what you get is the sum n equals 2 to infinity a n minus 1 x to the n minus 1. And the reason I pulled out the x is so that I can get these things to match, right? I have an n minus 1 here and an n here. I would like them to be both the same. But so if this, I'm summing up from n equals 2, this is the same as if I sum n equals, oops. Okay, my bad. I don't know. Sometimes I just write random junk. Yeah, so thanks for pointing that out. The exponent is 1. So again, this is just f of x minus a0 minus a1 x to the 1. This sum here can be rewritten. So imagine I plug in 2, right? That's a1 x to the 1. If I plug in 3, it's a2 x to the 2. So this is really just the sum n equals 1 to infinity. If I just kind of change the index, an x to the n. So what is this in terms of f? That's kind of similar to before, but actually maybe even a little bit easier because there's only 1 term missing. So this thing is just f of x minus a0. So I'm going to plug that in. So I'm going to erase this, and I'll just write here that this thing here is just f of x minus a0, and that's all being multiplied by 3x. And this one here, well, okay, what is, suppose so I'm going to take this whole thing here. So what is this in terms of f of x? So it takes a bit of thinking. You want to maybe factor something out and then change the index or something. But what is that? The thing in the pink box. Yeah, so I'll definitely factor out an x squared, because then that'll make these things match up. And once I factor out the x squared, then, yeah, so what should the index, so then the index will start at, I think, 0, right? I pull out an x squared. So, yeah, I can start at n equals 2 to infinity a n minus 2 x n minus 2. But if you think about plugging in 2, it starts, like, really this is starting at 0 because it's a0 x to the 0. So in terms of f, so it's actually just the function f. So it's x squared times f of x, right? Because this includes all the terms of f. And now I got this thing, which, okay, this thing's actually not that bad, because I'll pull out an x squared here as well, because why not? Just get these things to match. You don't necessarily have to do that, but eventually you're going to end up sort of doing that anyway. And then I can change the index, and I can write this as n equals 0 to infinity 2 to the n x to the n. So kind of as an intermediate step, right? So this is equal to x squared sum n equals 2 to infinity 2 to the n minus 2 x to the n minus 2. And if you think about where if you wanted to change the exponent to n, like if you want to change the index, like if I plug in n equals 2, I get 0 in the exponent, so it should really start at 0. So can anyone tell me what this is? Just this thing in the green box. So this is, yeah, bringing back stuff from a few weeks ago in generating functions. But yeah. Oh yeah. So if you include the x squared as well, then yeah. So this is, this whole thing here is x squared over 1 minus 2x. So the thing in the box specifically is like just 1 over 1 minus 2x, right? Because you can think of that as like, if I take what is 1 over 1 minus 2x, you can think of doing a substitution of some sort. And it's, 2 to the n x, sum of 2 to the n x to the n. Okay, so we've got this weird equation that involves f of x. But now actually, our life is kind of better because we can kind of solve for f of x in this equation. So we can solve for f of x, right? I can put all the f of x's on one side, factor them out, and then divide. So, okay, so maybe I'll just do that here. So if I wanted to solve for f of x, so I'll do that in this box. So what I get is, I'm keeping this f of x here. I'm going to move that over. I'm going to have to keep track of everything. So I'm going to put all the things without an f of x on the right side. But so I've got one f of x here. I subtract over a 3x f of x, and I add over a 2x squared f of x. And then the other side, I'm going to move this stuff. I've still got this 3x, so minus 3x a0. And I've still got my non-homogeneous term here. So plus x squared over minus 2x. So is that okay? So hopefully I got the same thing here. Looks okay. And in this problem, I gave you some initial conditions. So I told you that a0 is 1, a1 is 3. So I can plug those in. So I can just, change this to a 1, change that to a 1, change this to a 3. And then I can divide by my 1 minus 3x plus 2x squared. And then I've got an expression for f of x. So and that's great news, because that's, if I can kind of manipulate this and kind of try to understand what it is, that'll give me basically a formula for an. Okay, so, right. So if I plug in 1 here, so I got 1, this should be, plus 3x minus 3x. Because if I plug in a0 is 1, I get a 1 here. I get plug in a1 is 3, I get 3 here. And I plug in a0 is 1 again, I get 1 there. So the 3x's cancel, right? So basically what you get is this. So here I'm kind of, so I've got my 1 over this stuff, which I just get from this divided by the polynomial that's being multiplied by f of x. And then I've still got my non-homogeneous stuff here, which was this like x squared over 1 minus 2x. And now I've got that divided by this thing. But that's a formula for f of x, right? Which is a good sign because, like I said, f of x is the generating function for an. And so if we can kind of manipulate this equation, or we have this equation, if we can kind of play with the right-hand side until we can get the coefficient of x to the n, then that will be equal to an. So maybe I'll kind of, so this might look confusing. I've got this cancellation here. So these cancel, and on the top you just have a 1. Right, so how are we going to do this? Well, we need to do some sort of partial fractions, right? I don't see anything else that you can do. So to do that, we want to factor the denominator. And it factors like this. So 1 minus, so you can do this with the, whatever you call it, the binomial equation or whatever, but yeah, so if you factor the denominator, you get this. Okay, that's just usual quadratic stuff. So I can plug that in instead of the quadratic on the bottom. Okay, so here's what we end up with when I plug it in. So I've got 1 over 1 minus 2x times 1 minus x. And then on the other part, I have an x squared over 1 minus 2x squared times 1 minus x. So it's not completely clear what to do here. I mean, you could, so one possibility is you could just take each of these expressions and do partial fractions. And that's going to be fine. You can do that. It'll all work out. In this case, though, what I'm going to do is actually first, before I do that, I'm going to just combine these two expressions into a single fraction, which is kind of the opposite of partial fractions. But luckily, in this case, some things are going to cancel, which makes my life easier. So if I want to combine these two things, I need to multiply the first term on the top and bottom by a 1 minus 2x, right? Because that's what's missing in the denominator. So if I do that, I get on the top a 1 minus 2x, and on the bottom a 1 minus 2x squared. And I can now combine these fractions. So I get x squared minus 2x plus 1 over all this junk on the bottom. And now, kind of coincidentally or luckily, the top factors. So I can just write it the top as 1 minus x squared. That allows me to cancel with one of them on the bottom. And I've got this. So I can't guarantee that these things will always cancel and stuff like that. So you may have to, but you may have to do some more complicated partial fractions, but it's actually not that. I mean, yeah, it's slightly terrible to do the partial fractions for this one because it's you've got 3 terms on the bottom, but it's doable. But in this case, we got lucky and we had this cancellation. But we still have to do partial fractions anyway because, oh wait, yeah, so actually we don't need to, sorry. Yeah, so actually in general, when you see something like this, so when you see things on the, like some sort of expression where you have, I don't know, different things on the denominator, like so let's say you have something like this. In this kind of situation, you do want to apply partial fractions because you don't, it's not a form that we can really deal with directly. Or for example, if you had this, it's even worse, right? But here actually we can deal with this thing because we know how to, for example, we know what the expansion of this is, for example, right? And this is kind of a slightly more complicated version of the same thing. Is that clear? So is it clear how we got to this point? It's just mostly algebra. Yeah, so these tend to be a little bit complicated, but I think it's kind of nice because it shows you the power of these generating functions, because it allows us to solve some pretty complicated recurrence relations. Yeah, so is it clear what I'm going to do now? So I'm going to, I may as well just break this up. I think that's going to be the best way to do it. And I can kind of handle each of these two things individually. Okay, and then I can put them back together and it'll give me a formula for an. So let's do that. Right, so I break these two things up, this thing up into two things. And yeah, there's a sort of natural substitution that's sort of begging for you to do it here, right? That I should let y equals 2x. So then if I look at this first term, this first thing, I have 1 over 1 minus 2x squared is 1 over 1 minus y squared. And that's a sort of thing that we know how to deal with. So this is sum n equals 0 to infinity, n plus 1 y to the n. For example, if you wanted, you can do that by saying, okay, 1 over 1 minus y squared, right, is the derivative of 1 over 1 minus y, which is, the sum of the derivatives of, y to the n equals 0 to infinity. And if you do a bit of manipulation, you get this, right? So this is something we've seen a lot of times before, but you have to be good at recognizing these things. And then I can plug back in for x. So I get, it's the sum n equals 0 to infinity of n plus 1, 2 to the n, x to the n. And this other thing is practically the same thing because it's just the same thing times x. If I take this thing times x, it kind of shifts my exponent here to an x plus or an n plus 1. So it's the sum n equals 0 to infinity, n plus 1, 2 to the n, x to the n plus 1. And if I want to kind of get that back into an exponent of n, I can just change the index. And if you kind of think about how that works, so if I do my index from 1, then here I should have n minus 1, and n. So kind of all of your n plus 1s become n, and your n's become n minus 1. Okay, so we're done, actually, believe it or not. So what is f of x? So remember we said f of x is equal to this thing minus that thing. So what we have to do is we have to say, okay, so we have to take this thing in this pink box, so pink, the thing in the pink box, minus the thing in this blue box, and that's f of x. Now you have to be a little bit careful with the indices because this one starts at 0 and that one starts at 1, but that's kind of fine. So you can just, for example, take the 0 term here, which is 1, because if I plug in 0 here, I get 1 times 1 times x to the 0, so I get, so it's just 1. This 1 here is for the n equals 0 term here. And then for all the other terms, n equals 1 to infinity, I have this thing minus this thing times x to the n. So all of this, everything that I'm doing here is just a bit of algebra, but really this is your answer. That this is an is equal to this for all n at least 1, and a0 is 1. But actually, if you think about it, if you plug in 0 here, I think you actually get 1 anyway. So actually, this is valid for all n at least 0. So all of the rest of this is just simplifying, which if you were doing an exam or an assignment, you don't have to simplify it. It's totally fine to just leave it like this. But if you wanted to write it in a slightly prettier form, you get this. But that doesn't really matter. So are there any questions about this? Practice makes perfect, okay? So you will be asked to practice this on your 5th assignment. So I think you already have the 5th assignment, right? So you can already practice it there. But like with everything else, the assignment is going to give you some practice, but if you really want to get good at this, and it'll help you on the test if you practice separately. So I've posted some practice for the 3rd test. So that can give you some practice. There's also the practice problems. There's a link to that on the course webpage, and there's also the textbook, which has solutions to the odd numbered questions. So so this was just one example. But generally, so what I did here can work for a lot of different problems. Okay, so let me kind of recap what the steps were. So you're given some recurrence. You want to solve it. You can define f of x to be so suppose this is a recurrence for an. You define f of x to be the sum of an x to the n. Now, what you can do is just write down the recurrence for x to the n, for an, multiply both sides by x to the n. Okay, those were our first 3 steps. And then just take this recurrence and sum it up over all of the values of n for which the recurrence is valid, right? Because when I write down, for example, in our example, we wrote down like an equals 3, an minus 1, whatever, minus 2, an minus 2, plus 2 to the n minus 1 or something. This is only valid for n at least 2. So therefore, our sum was from n equals 2 to infinity. Because, so you sum up both sides of the equation from n equals 2 to infinity. And then it all comes down to algebra, okay? So you take these parts of this sum, you write them in terms of f of x. So it might be, for example, if you're summing from 2 to infinity, it might be you get f of x minus a0 minus a1x as one of the things. And, so basically you write everything as much as you can in terms of f of x, you solve for f of x, and then you do a lot of algebra, partial fractions, and then try to recognize the things that we know how to represent. So, canceling, partial fractions, blah, blah, blah. Okay, so this is a general kind of recipe for how to solve these second order linear non-homogeneous recurrence relations.